In this video, we're going to be looking at projectile motion. So I'm going to start off talking about projectile motion with a little discussion on scalars and vectors. So we would have covered these in, say, stage 1 physics, but if we haven't, we'll just have a quick run through now. So, a scalar quantity is something that only has a magnitude. So that is distance or speed. I could say that I am running at 16 meters per second, which is actually very fast. But you have no idea which direction I'm going. I could be running south, east, north, west, anywhere. So that's a scalar quantity. It's only a magnitude. Now, a vector quantity is different. A vector quantity has a magnitude and a direction. So it has a size to some description. So I could say my 16 meters per second. And it also has a direction. So I could be, okay, I won't be running because 16 meters per second is crazy fast. I could be driving a car at 16 meters per second in a southeasterly direction, and that will give me a direction as well as a size. I can represent a vector quantity with something that we call a vector, which is just an arrow basically. And the size of this arrow is dependent on the magnitude of my vector quantity, and the direction of this arrow is dependent on the direction. Who would have thought? So that's a scalar quantity and a vector quantity. So in, say, stage 2 physics, a vector quantity in an equation has a little arrow above it. So that little arrow denotes that it's a vector quantity. So now moving on. If we're talking about a velocity, and a velocity is speed with a direction, that is a vector quantity. If I have a motion of something moving along, so for example here I'm throwing a dart. Now if I was to draw the vectors for the motion of this dart, we'll see that it goes slightly up and slightly down. So that tells me that the velocity of the dart is made up of two components. We have a component of the velocity of the dart in a horizontal direction, and we also have a vertical direction. So the sum of those two vectors gives us the resultant, which is the one that we see, the one that's on an angle. So if we get a vector, we can break it up into its two components, since we're dealing with motion in 2 dimensions. If we're dealing with motion in 3 dimensions, which you don't in Sace, it'd be a third dimension. But in Sace, we deal with motion in 2 dimensions, so we break up the vector in its two components: the x-axis and the y-axis, or the horizontal motion and the vertical motion. So when we draw in the two components of any vector that we get, we can start analysing motion in solely the horizontal direction and motion in solely the vertical direction. So this is very important when it comes to calculating key points of the motion later on. So now that we've broken up our motion of my dart into its components all the way along, we'll see that the horizontal motion, if we neglected air resistance, would be exactly the same across the whole motion of that dart. That's because of Newton's first law of motion. An object in motion will stay in motion. So if I didn't have an external force acting on that, which would be my air resistance, that horizontal motion of that dart will continue to go in the same magnitude, in the same direction as it did before. So any horizontal motion that we see in, say, stage 2 physics will be neglecting air resistance unless stated otherwise. And as such, we can say that the horizontal motion at the start of an object moving, of a projectile moving, will be the same as the horizontal motion at the end of that. The vertical component, on the other hand, has gravity acting on it. We see that in my dart case, it goes up and down. So gravity is always acting towards the centre of the Earth, And in any case that we see on a small scale, it acts directly downward. So the acceleration due to gravity is 9.8 meters per second squared. And we use this in key calculations, again, which you'll see in another video. So, from our vector components, if I have a vector, I can break it up into its two components, horizontal and vertical motion. The horizontal component of a velocity remains constant throughout its motion if we neglect air resistance. The vertical component has the acceleration due to gravity acting on it, and as such, the vertical component of the velocity is changing. We can calculate the size of this velocity at any point in motion using some equations, which we'll get into later. The horizontal and vertical motions are independent of each other. Any changes made to the vertical velocity of an object cannot make any changes to the horizontal velocity. This is because the vectors are perpendicular or 90 degrees to each other. And any vector that is 90 degrees to another vector cannot make any changes to that vector. So any acceleration in the vertical direction, which is the acceleration due to gravity in our case if we're dealing with motion on Earth, makes no changes to the horizontal motion. The horizontal component remains exactly the same throughout the motion if we neglect air resistance. The vertical component changes due to the acceleration due to gravity. I've already talked a lot about these horizontal and vertical components of a vector. But how do we get a horizontal and vertical component? So if I draw a vector and then I join up a vertical arrow and a horizontal arrow, if we go from the tail to the head of the horizontal and we connect that head to the tail of the vertical, the direction of this resultant vector is coming up towards my head. So that's how we draw in the two components. If we then want to find out the magnitude of these components, we can then apply trigonometry. So this is a right angle triangle. If I have an angle, so if I call this angle down here, theta, and I'm going to give theta a magnitude of say 30 degrees, knowing that angle and knowing the magnitude of this vector here, we can calculate any one of these sides. So this is using simple trigonometry. So if I call this long vector here, the resultant vector, 25 meters per second, I'll have an angle of 30 degrees. We can find out the magnitude of our vertical component using trigonometry. So in this case, you can use sine theta is equal to opposite over hypotenuse. Rearrange to find the size of this component. If I wanted to find the magnitude of the horizontal component, I would use, in this case, cosine. Cosine theta is equal to adjacent over hypotenuse. So the hypotenuse in this case is going to be my 25 meters per second of my resultant vector. My theta is 30 degrees. If I substitute that in and rearrange, I can find out that my sizes are as such. So that's how we find out the components of our vector. Now, I made it fairly clear that my horizontal component of my velocity does not change over the motion if we neglect air resistance. But what happens if we do include air resistance? So, normal path without air resistance would be a nice parabolic curve. Whatever it starts with would look exactly the same as whatever it ends with. Nice, perfect curve. This is not the case we see though, because we have air resistance in almost every case that we have on Earth. So we're going to have a curve that looks more like this. it drops off fairly quickly towards the end, and we see that the start is not the same as the end. So there's the effect of air resistance on the range of our projectile. We see we get a lot of a reduced range, and the horizontal component of my velocity actually decreases over time. So to summarise, a vector can be broken up into its horizontal and vertical components if we're dealing with motion in 2 dimensions. If we're dealing with a velocity vector, the horizontal velocity does not change over the path of the projectile. The vertical motion, however, does change due to the acceleration due to gravity. The acceleration due to gravity is 9.8 meters per second squared. We can calculate the size or our magnitude of our components using trigonometry. So you need to remember sine, cosine, and tangent ratios in order to find out the magnitude of these sides. By neglecting air resistance, we get a parabolic path that our projectile takes. If we include air resistance though, the range or the distance travelled from start to finish is quite dramatically reduced due to air resistance. We do not need to calculate the effect due to air resistance, we just need to know about it. So that is a simple basics on projectile motion. I would also do another video on calculations involved with this. The calculations can be a little bit tedious at times, but it's all fun and games as part of physics. Enjoy!